Let's say you have a piece of paper, and on that paper you make a checkerboard. And within one of those squares, you use a white crayon and make an invisible mark on that paper, and you want to figure out where that mark is. Now, I've demonstrated that it's really easy to use a device like this, a portable near-infrared spectrophotometer, for determining where that mark is. Let's say you use a crayon or use an invisible ink. That's actually really simple for a tool like this to detect. But how do we do this algorithmically? How do we take all of the data and determine where that outlier is? So in this video, I want to demonstrate how we can use the local outlier factor algorithm for our outlier detection. And this algorithm uses a density-based technique somewhat analogous to dbScan that I've shown previously for predicting if a sample is an outlier. If we go to scikit-learn and we look up LOF, we can see that we have some example use cases, but importantly, it's usually really good to look at the figure. Just let's look at how the outliers are determined. And you can see here that when we have a cluster of points, these points will be considered inliers. And based on the radius of the red ring, it is not very likely that those points are outliers. As you move further away from these two centroids, you can see that the further points have a larger ring, and that's how they are determining the likelihood that a sample is an outlier. Now, we're not going to use this, but we can at least see visually how this technique will work. So I want to demonstrate how we can do this with analytical data. So I'm going to demonstrate how a chemist will find this hidden mark. Like many videos before, I have a lot of libraries that I will import for this video and a couple other projects I'm going to work on. And I've also generated a set of data that we can use to find my white crayon mark. Next, after importing the various libraries that we need, I'm also going to import the data, and we have a path to the data. I will show you what that looks like. If we type in scaled data, this is data that has already been scaled. And look at the first 5 rows. You see we have our spectrum ID and several wavelengths related to the near IR range due to our spectrophotometer. Now, if I take this data and transpose it and then plot the data, you can see we have several points here and one that already appears to be an outlier. So visually we might expect 5146838, this orange trace here, to be the outlier. But let's actually measure this and use an algorithm to confirm our visual hypothesis. So to build our outlier model, we're going to import from scikit-learn neighbors the local outlier factor. We're going to take our scaled data frame. This data frame has already been exposed to our apply SMV method, and we're going to copy that and store that as df_field. Next, we're going to instantiate our local outlier factor with an n neighbors of 5 and a contamination of 0.5. The contamination is an estimation of how many outliers we might expect, or a proportion of the samples that we expect to be outliers. And we're going to instantiate that as LOF. And then we're going to use that model to then fit and predict df_field and create a new column within df_field called outlier. Next, we're going to use the getOutlierRow and map that using this little function here, just so we can have a cleaner printout. When we do that, you can see that we have one outlier that was detected, and we can see that that outlier was detected in row 2. So that is what this little function is doing. It just allows us to better interpret the results in the context of our data frame. Next, we're going to plot the outlier data using PCA. So PCA is a great technique for decomposing the data. So we have data that's multiple dimensions, and we can try to summarize all the data within 1, 2, 3 dimensions, which is much easier to visualize. In this case, we're going to instantiate using 2 components, and then we're going to take our scaled data frame and use our outlier map to then color the marks, whether they're an inlier or an outlier. And you will see that that is what this map function is doing. And then we're going to enumerate and create our figure. When we plot this data using PCA, we can see that many of the samples are inliers. We can see that they all cluster to the left side of the figure, and we have our outlier point over here, which is very, very different. And this would suggest that the second square of our checkerboard is where we had our outlier sample. Visually, this is very easy. Using the LF methodology, we can see that this was also very consistent. You can imagine that if we were to adjust the contamination parameter, these points may also be considered outliers, but based on what we expect within this data, we can sort of inform the model. But importantly, we want to also understand what's driving this separation. And earlier on, we saw that there were some peaks around 1700 and in the 2350 region, as well as some of these others that are maybe indicative of whether we have an outlier or an inlier based on these results. And so I want to see if we look at the loadings plot that was generated from the PCA, that will give us a better idea of what's driving this separation, particularly along PC1. So when we do that, we're going to extract the wavelengths from scale DF and convert those into a float data type. And then we're going to take from PCA.components underscore, we're going to use the 0th components, which would be consistent with PC1, and store those as loadings components underscore PC1, and then plot that data. When we visualize that, we have this region around 1700 nanometers, plus or minus maybe another 100 nanometers, and then we have this region around 2250 to 2350 that's also elevated in PC1, perhaps suggesting these are the regions that are really driving that outlier sample away from our inlier samples. I've also added a color map here that if a signal is above a certain threshold, in this case 0.03, it will be red to help us to understand the relationship between that NIR spectrum and this data point here. If you would like the data that you saw in this video, let me know in the comments, or if you want me to upload this notebook, also let me know. This technique is very suitable for many other analytical methods or other types of engineering and consumer data as well. If you like the video, like, comment, subscribe, and I'll see you in the next one. Peace.